Hi everyone, I'm Rowena. I'm a PhD student here and I'm also a pulsar timer. So today I'm going to tell you a bit about pulsar timing and the gravitational wave background. Um, mm. so normally I'd start this talk with pulsar timing 101 and explain how we time pulsars from pulsar emission at the pulsar to radio telescope to data analysis. But I only have a short amount of time, so you should just know that we're really good at timing pulsars and pulsars are really good at keeping time. And if you don't believe me, here's a timing solution. So what a timing solution is where we make a model that kind of tries to take into account every single thing that could change the time when the pulse arrives. And once we have that, we predict pulse arrival times, and then we measure the pulses and see when they actually come. And so the x-axis here is in days. So this is about 2.5 years of data. And you can see on the y-axis, that's our residuals from the timing model, so the difference between the arrival time and predicted time. And you can see that we're in the microseconds regime. So the average error is about 1.4 microseconds. And this is actually a pretty not well-loved pulsar at the IPTA, the International Pulsar Timing Array Conference. It was the collaboration's least favorite pulsar, but it's my favorite pulsar. But some of them are down on the scale of like nanosecond accuracy. So we're really good at timing pulsars. And so this talks more about the gravitational wave background than it's about pulsar timing. But as you can imagine, gravitational waves are perturbations in space-time. And so if they change the amount of space between us and the pulsar, we should be able to detect that. And so that brings me to detecting the gravitational wave background. And so we've heard a bit about gravitational waves throughout this conference so far, but to my knowledge, all the gravitational waves we've been talking about are down this end of the spectrum. So we're talking about gravitational waves of periods of about seconds that we can detect with our ground-based detectors like LIGO in the US. But when we're talking about gravitational wave detection with pulsar timing arrays, we're talking about gravitational waves with a period of years. And we effectively build a galactic scale detector. So it kind of works with a similar mechanism to your 4-kilometer long laser arms in the US, but it's the size of the galaxy. And so in here, you're measuring the change in distance between the mirror and the laser beam. And here you're measuring a change in distance between the Earth and the pulsars. Yeah. Okay, and so how do we actually do that in practice? The first thing that we're looking for when we're detecting a gravitational wave background is a common red noise. So you want to have a time correlated noise process coming through your timing residuals. And so in real pulsars, that looks something like this. This is a graph of the residuals from pulsars from the Parkes Pulsar Timing Array that came out in the data release last year. And you can see some of these pulsars have really quite prominent red noise processes where they're changing in a time correlated fashion. And this is like, I guess, much neater, kind of nicer simulation where you can see that. You can see they all have little wiggles in them. And that was kind of the first thing that came during the second data release as evidence of the gravitational wave background. But there are lots of different processes that could cause potential red noise, that could cause a time correlated variation. And so what we really need to be looking for is the spatial correlations in our residuals. And so the way we do that is look for a specific kind of angular correlation. So if you have your pulsar timing array and maybe 2 example pulsars here, you measure an angle between the 2, and then you look at the timing residuals and how correlated they are, and you plot them on a plot like this. And so you would expect that pulsars that are in the exact same direction to be almost entirely correlated if they're being affected by the same gravitational wave signal. And then pulsars that are in opposite directions are also quite correlated. And then ones at 90 degrees are anti-correlated. And so that would look probably like this quadrupolar signal here in the dark pink. But the real kind of thing that we need to show that we've detected a gravitational wave background is this Hullings and Downs curve, and that comes from fun effects from photons riding on gravitational waves and things like that. And so the Hullings and Downs curve is known as the smoking gun of gravitational wave background detection. If we have a common red noise and we can see this spatial correlation, then we can be quite confident that we've detected a gravitational wave background. And so then I guess that begs the question, have we done it yet? And so you might have seen there was lots of hype in June last year when there was a coordinated release of data from the International Pulsar Timing Array. And all of the kind of constituents in the IPTA released their own data sets and their own evidence for the gravitational wave background. And here's a summary of what the different PTAs have reported. I think kind of the first key takeaway from this is that 5 sigma is usually the threshold for detection, and these are all below 5 sigma. But there's still exciting, strong evidence for the gravitational wave background, and hopefully as we continue getting more sensitive measurements, we will cross that detection threshold. So the PVTA is the Australian collaboration. We had a 2 sigma significance, so we were on the more conservative side. But I don't know where I was going at with that. I guess we're very conservative about how we do our noise modeling. We don't want to claim detection if we don't really have one. Then you have the European pulsar timing array, Nanograv, which is the American collaboration, and the Chinese pulsar timing array. They're currently reporting the highest significance, but they haven't released much detail on that. They haven't released their data and things like that. So we're kind of waiting to see how they got that result. And then this one here is the Meerkat pulsar timing array, which is this telescope I have down here. It's a radio telescope in South Africa, and it's one of the most sensitive radio telescopes we have at pulsar timing at the moment. And that data release is coming soon, so I would be very excited for that. Also just want to point out these data sets are not independent. They all share pulsars across the sky, so that's something to keep in mind. Okay, and so why am I telling you about the gravitational wave background? Well, I'll get to my research in a sec, but there's lots of reasons why the gravitational wave background is interesting. So I guess this is quite a new phenomenon because we've only just attempted to really measure it properly for the first time. But there are a couple of different potential sources of the gravitational wave background, including supermassive black hole binaries. So you have lots of them in all different directions, and the signals all kind of overlap into this stochastic gravitational wave background. You could have an individual supermassive black hole binary that's making a more distinct signal than the others, but it also could potentially come from more fun exotic things like phase transitions in the early universe and things like that. And so if the gravitational wave background arises from that kind of source, it may allow us to probe the early universe and can also give us some clues about how things are arranged. Yeah, so that brings me to my research. I've got a fun thing. Okay. So I'm trying to currently work on developing ways to understand what the source of the gravitational wave background is. And there's, differentiating between the 2 main lines of thinking. Is it supermassive black hole binaries, or is it early universe physics? And the key to unlocking that is going to be cosmic variance and isotropy. So I showed you the Halling's and Dowden's curve before, and I told you that that was the correlation between pulsars that we're looking for. But in all reality, depending on when you take your measurement of the gravitational wave background in time, it's going to have some random variance. And I've just kind of tried to demonstrate that here with the different waves adding up. So when we measure the gravitational wave background, we're not going to actually measure exactly the Halling's and Dowden's curve. We're going to measure some angular correlation function that's close to it. And so I've been working on some simulations, and every single one of these pink curves that you see here is an isotropic gravitational wave background. So the same in all directions. And so you can see that there can be quite a bit of variation away from the Halling's and Dowden's curve. And this is something that we need to model in our pulsar timing analyses, and it also is important to keep in mind when we're looking at angular correlation function plots. But the next thing to kind of look at is how would this plot look for an anisotropic background? And can we use the measurements that we currently have of the gravitational wave background to determine if it's isotropic or not? And then what would that imply about the source? But I kind of got shifted off this the theoretical how we understand the gravitational wave background, because the Meerkat pulsar timing array data release is imminent, and they need to make maps of their gravitational wave sky so they can see what the gravitational wave background looks like as seen by Meerkat. So at the moment, I'm working on making maps of the gravitational wave background for them, and we're trying to understand the sky. The first data release, I think, will be out sometime this year, and I think it's looking to be the most sensitive pulsar timing measurements we have so far to date. So it could be quite an exciting announcement, and we're kind of focusing at the moment on a search for anisotropy, given it's the most sensitive gravitational wave background measurements likely made so far. We want to try and see what that looks like. And so sky maps have been made before. This is a sky map from the Nanograv paper, but this is actually an isotropic background, so there can be quite a lot of variation in maps even when you do have a purely isotropic background. So we're also developing a framework for developing our confidence in any claims of anisotropy or isotropy. I can't really say anything about it yet because none of it's released. But here's a sky map that we've made on some simulated data with no noise in the pulsars. So you can see it makes a really beautiful Hullings and Downs curve, and the signal to noise is quite boring. Yeah, that's all I can say about the gravitational wave background as seen by Meerkat. So hopefully you understand a bit more about the gravitational wave background, the data releases that have happened so far and where we're at. And if you have any questions, please ask them now or feel free to contact me.
So when you're talking about the isotropic background, are you talking about the gravitational wave being actually isotropic, or do you mean the sources are distributed isotropically but still be discrete sources? Does that make sense?
No, that does make sense. I think when I say isotropic, I mean that there's no really obvious single source. So it could be supermassive black hole binary individual point sources distributed isotropically, and there's many of them, so we can't tell them apart, or early universe things, which would also be isotropic. But there is a potential for there to be a continuous point source in that signal as well, which would be different.
Can I follow up? So then, if you are doing that, then what would be the expectation? Would the degree of anisotropy be different for point sources like supermassive black hole binaries compared to things from the early universe? Like, would you expect one to be more isotropic than the other?
So the universe would be, early universe physics would be entirely isotropic, we would expect, similar to like the cosmic microwave background.
Even with phase transitions and stuff like that?
I think so.
Okay, I don't know much about it.
Yeah, because it's when we're talking phase transitions, we're talking just after Big Bang, so it should be the same in all directions that we look.
Okay, sure.
Yeah, and then the point source question really depends on how many point sources there are that we're seeing in our data. If there's 4 of them, maybe we'll be able to disentangle them, but if there's 100, probably not. But I guess that's still an open question. Like I said, we want to kind of understand how maybe 4-point sources would affect the angular correlation curve, and if you can measure a difference between that and isotropy. Yeah,
Thank you.
No worries.
I know it's like your real results aren't out yet, but in the ones from Nanograv, like how you get this map.
Oh, the map from Nanograv.
Yeah, so I mean, is that understood what that variation on the sky is? Or is that just
I don't know a lot about how the Nanograv maps were exactly put together because their code isn't super public. So I don't know if this is a dirty map or a clean map, which means I don't know if it has the antenna response function in it or not.
That's what I'm asking. Could that stuff be real, or is it definitely noise and some? And if it's noise, is it understood?
They claim it's noise. I don't know if it's understood.
But then do they understand why?
I don't know. I don't think so. Yeah, it could be
What are the red spots?
oh, sorry, the red spots are the pulsars. In the Nanograv timing array, and then these are our Meerkat pulsars, which are mostly in the southern sky because Meerkat's in South Africa.
Would the next speaker come up, please?
Isn't it a little bit?
Sorry. Okay. Last quick question.
Isn't it a little bit strange to go back to that previous one? The brightness patterns seem correlated where the pulsars are. I would say just for the eyeball, it looks to me like where you have lots of pulsars, you have lots of brightness.
Yeah, except that I think this is power, so it's actually brighter in those darker portions. But like I said, I'm not entirely sure if this accounts for the antenna pattern function of the pulsar array in this plot. It's not entirely clear, unfortunately. Yeah, thank you.